Optimization. In optimization problems, the goal is to maximize or minimize something, like volume, area, or cost. For each problem, you will need an equation for what you are trying to maximize or minimize, and then a second equation called the constraint equation, because there are always restrictions in life. We only have so much material. So this is used to plug into the first equation so that there's only one variable. Then you will need to differentiate the equation, find the critical values, and answer the question. Alright, here we go. You have been asked to design a 1,000 centimeter cubed can shaped like a right circular cylinder. What dimensions will use the least material? So what I'm going to go ahead and do is just go ahead and draw a right circular can, a right circular cylinder. And we're talking about its volume. We're told that the design needs to be 1,000 centimeters cubed. We're talking about the dimensions. So I'm going to label the dimensions as R and H generically, the radius and the height. And what we're trying to do is minimize surface area. So the surface area, I'm going to go ahead and call S for surface area. I have to write an equation that represents the surface area of this right circular cylinder. So the top and the bottom are both circles, so the area of a circle is pi r squared, but there's a top and a bottom, so 2 pi r squared, plus the surface area is the entire can all the way around. So if I think about that for a second, if I cut the can down the side and unraveled it, it would look like a rectangle. So the side of the rectangle here would be that height h, and then all the way around, which is this base here of the rectangle, would be the circumference of a circle. And the circumference of a circle is 2 pi r. So that means that the surface area is 2 pi r(h) of the area around the side of the can. So plus 2 pi r(h). So this is the equation that we are trying to minimize. Now currently it has two variables in it. I have r and I have h. So what I want to do now is think about my constraint equation. I have a restriction. The design has to be only 1,000 centimeters cubed. That's a volume. So I have my constraint equation. So we're going to start out with the generic volume formula, which is pi r squared h, but we know the volume is 1,000. So 1,000 pi r squared equals pi r squared h. So what I'm going to go ahead and do is solve this constraint equation for h. So I'm going to divide by pi r squared on both sides. So 1,000 divided by pi r squared is equal to h. And then I'm going to go ahead and take that quantity and substitute it in over into the equation I'm trying to minimize so that it's all in terms of the same variable. So now I want to go ahead and simplify this, so I end up with 2 pi r squared plus I'll have 2,000. The pi's will cancel and an r will cancel, so 2,000 over r. Now that's all in the same variable. I want to be able to take its derivative, so before I do that, I'm going to do one more thing. I'm going to write 2 pi r squared plus 2,000 r to the negative 1. So I can apply the power rule to take the derivative. So my derivative, s prime of r, I'm taking the derivative with respect to r, is 4 pi r minus 2,000 r to the negative 2. And I'm going to need to rewrite this as a rational expression. So I have 4 pi r minus 2,000 over r squared. And I want that common denominator of r squared, so I'll multiply the top and bottom by r squared, and I'll end up with 4 pi r cubed minus 2,000 over r squared. And I want to know, where is that equal to 0 or undefined? So it's equal to 0 when the numerator 4 pi r cubed minus 2000 is equal to 0, and undefined where r squared, the denominator, is equal to 0. So here we have pi r cubed would equal 500. Divide by pi, I get r cubed equals 500 divided by pi, or r is the cube root of 500 over pi. And over here I get r equals 0. However, it doesn't make sense for the radius to equal 0 if we're going to have any volume on our can. So r equals 0, this quantity doesn't make any sense. So this is not a critical value. So my only critical value is this cube root of 500 over pi. Now, since this is a critical value, we do want to justify that this is in fact a minimum. So we're going to go ahead and apply the second derivative test here. So I have s double prime of r, so I'm going ahead, this is s prime, I'm taking the derivative. I'll get 4 pi and then plus 4,000 r to the negative 3, or 4 pi plus 4,000 over r cubed. But the only thing is the r values are the radius of my cylinder, so r has to be greater than 0. So what that means is that for any value of r that I substitute in here, since this value is positive, the second derivative is always positive. So if the second derivative is always positive, so I know that s double prime of r is greater than 0 for all r greater than 0. So s must be a concave up function. And we can apply the second derivative test, so we know that any critical value must be a local minimum. So by the second derivative test, so I'm going to say by the SDT, our function s of the cube root of 500 over pi is a minimum. So we've justified it, we've showed that this is a minimum, but now we have to make sure and answer the question. The question asked us what dimensions will use the least material. So the dimensions are the radius and the height. Well, we found the radius, so the dimensions, the radius would be the cube root of that 500 over pi, and the units there are centimeters. So we also need h. We also need the height. Well, here's what we know about the height. The height from our constraint equation was 1,000 over pi r squared. Well, we don't want to leave our answer with r in it. We can now replace r with our value, the cube root of 500 over pi. So our other dimension is 1,000 over pi times the cube root of 500 over pi squared. So these are the dimensions that use the least material. So least material means minimize that surface area. And we want to make sure and include centimeters. In this next example, we're told a poster is to have an area of 180 inches squared. So I'm just going to pause right there. That's our constraint, that's our restriction. This area has to be 180 inches squared. With 1-inch margins at the bottom and sides and a 2-inch margin at the top. What dimensions will give the largest printed area? So let's go ahead and draw a picture. So here we have a rectangular poster, and I went ahead and called the entire base of the poster X and the entire height of the poster Y. And then I also went ahead and labeled these 1-inch margins on the sides and on the bottom, and this is a 2-inch margin on the top. So I'm actually going to start this one by writing out the constraint equation first. So the constraint equation on this one is going to be that the area, which is x times y, is 180 inches. So 180 is equal to x times y. And now let's go ahead and talk about what exactly it is we're trying to maximize or minimize. So what dimensions will give the largest printed area? So we are trying to maximize something, largest, the area of this inside region here. Alright, so maximize the printed area. I'm going to call this function A, and I need to go ahead and find the base and the height to find the area. So the base of this inside shaded region here, well, if the whole entire base is x, and I'm going ahead and taking away 1 inch from the left side and 1 inch from the right side, this inside part would be x minus 2. And then if I wanted the height, so the entire side is y, but I'm taking 2 off the top and 1 off the bottom. So this inside portion's height is going to be y minus 3. So the printed area I'm trying to maximize has dimensions base x minus 2 times height y minus 3. So notice it's a function of two variables, x and y, and that's where our constraint equation comes in. So I'm going to solve the constraint equation for the variable y. So I'm going to divide both sides by x to get y equals 180 over x, and then I'm going to substitute that in over here to the y variable. So now notice that a is a function of just x. I have x minus 2, 180 over x minus 3, and I want to take the derivative, but first I'm going to go ahead and distribute this out to make it easier to take the derivative of. So I'm going to have 180, the x's will cancel, minus 3x, minus 360 x to the negative 1, because I'm going to have inside here this 360 over x, so I'm writing it as x to the negative 1 plus 6. So now when I take the derivative, I will have a prime of x is equal to negative 3 plus 360 x to the negative 2. So now we simplify that to negative 3 plus 360 over x squared. So I would make the denominator here x squared, the numerator x squared. So we are going to set negative 3x squared plus 360 over x squared equal to 0, or undefined, to find my critical values. So to set equal to 0, I'll set the numerator equal to 0. And I end up getting x squared would equal 120, or x equals plus or minus radical 120, or x equals plus or minus, 2 radical 30. And we know that it doesn't make sense to have a negative x value because x was the side length of the base of the poster. So we only have x equals positive 2 radical 30 as a critical value. And to determine where the derivative is undefined, we set x squared equal to 0. So we get x equals 0, but that doesn't make sense. We can't have the base of a frame equal 0 and still manage to have any area involved. So my only critical value is 2 radical 30. We want to go ahead and show that at this critical value we have a maximum, since we're trying to find the largest printed area. So to show that we have a maximum, we're going to go ahead and use the first derivative test. We're going to create our number line, and our number line is going to start at 0 only because this is for x values, and we already said x has to be positive. So our number line will be from 0 to infinity. Our critical value is 2 radical 30. So we can pick our test point of, let's say 1, and then a whole number bigger than 2 radical 30 is going to be 13. So if we substitute these test points into a prime, that will tell us about a. So if I substitute in 1 into my derivative function here, I'm going to go ahead and get out a positive number. So the bottom is always positive. If I plug in 1 into x squared here, overall the numerator will be positive. So A is increasing on that first interval. If I substitute in 13 into this x, I'm going to end up with a value that's negative and bigger than 360 in magnitude, so that means I'm going to end up with a negative, so I am decreasing. So I can see that I'm going to have increasing to decreasing. By the first derivative test, I would have a local maximum, but since this is the entire function here, I can see that this is really going to be my absolute maximum. So I have a max occurring at the x value, so at x equals 2 radical 30. But now we have to make sure and answer the problem. The problem said, what are the dimensions that will give the largest area? So the dimensions that will give the largest area are x equals that 2 radical 30 inches, and then remember from the constraint equation, y was 180 over x, so that's 180 over 2 radical 30, or 90 over radical 30 inches. So the other way we could potentially see the answer is dimensions are given as 2 radical 30 inches by 90 over radical 30 inches. In this example, we have a field with an area equal to 1,400 square yards is partitioned as shown in the diagram. What is the minimum amount of fencing needed to create the portioned field? So we are trying to minimize the amount of fencing that we have here. So that's what I'm going to start by writing down. We want to minimize fencing, which is essentially like minimizing the perimeter. It's not exactly perimeter in the way we would traditionally think about it, because that would mean just like the outsides, but we really mean all of these pieces of fencing here. So we're minimizing fencing or perimeter, and what we have is we have information about the total area. So the area has to be 1,400 square yards, and so that's our constraint. So our constraint is on area. We're trying to minimize the amount of fencing, but we have to create this field with 1,400 square yards total. So let's go ahead and write an equation for the perimeter using the given variables that are involved in the diagram. So because I'm referring to it as perimeter, I'm going to call it P. And the variables over here are W and H. So we have a total of 6 copies of W, so 2 across the top, 2 across the middle, and then 2 across the bottom that make up the perimeter horizontally, so 6W. And then when we think about the perimeter or the fencing vertically, I have HH on each side, and then 3 extra copies of H in the middle for fence lengths, so a total of 7 copies of H. So right now, my primary equation that I'm trying to minimize has 2 variables. So that's where we need a constraint equation that also relates those variables so that we can solve it and replace one of the variables over here to make it all in terms of the same variable. Now our constraint is, as I said, on area. So we have 1,400 has to equal base times height, or length times width. So here we have 2 copies of W as the base, and then we have 2 copies of H as the height. So 1,400 has to equal 4WH. All right, so now we are going to go ahead and solve this equation for either W or H. So I'm going to go ahead and solve it for W. So we have 1,400 over 4H is equal to W. And then 4 goes into 1,400 350 times. So we have 350 over H is equal to W. And now I can take that and plug it into my primary equation so that my primary equation will just be a function of h now. So I'm going to replace this w with 350 over h, and then we have plus 7h. And so now, if we multiply this together, we get 2100 h to the negative 1 plus 7h. And I'm writing it like this because I'm going to need to find the derivative. In order to find a minimum, I need to find those critical values. And so those are found by setting the derivative equal to 0 or finding where the derivative is undefined. So we're going to take the derivative now. P prime of h is negative 2100 h to the negative 2 plus 7. And I'm going to need to set that equal to 0 to solve for h. So I'm going to scoot everything up a little bit here. If we subtract the 7 to the other side and divide by negative 2100, that's got to equal h to the negative 2. The negatives will become positives. 7 goes into 2100 300 times, so I have 1 over 300 is equal to 1 over h squared. So h to the negative 2, 1 over h squared. If I flip both sides, I get 300 equals h squared. And let's move this up a little bit more. So h is equal to plus or minus the square root of 300. But because we're talking about h representing height, it's got to be the positive one only. So we're thinking positive radical 300, which is 10 radical 3. So this is my critical value, right? And so we wanted to know, see if I can zoom out a little bit, see everything here. No, maybe not. What is the minimum amount of fencing needed to create the portion field, right? So minimize that perimeter. So it's going to happen where h is equal to 10 radical 3. We should take the second to prove that this is a minimum. I mean, it is the only critical value. But to prove that it's a minimum, the easiest thing to do would be to take the second derivative and show that that's always positive, because then any critical value will be a minimum value. So we can show that it's a minimum. So show h equals 10 radical 3 is a min. If we take the second derivative, that's going to be, so I'm looking right here at the first derivative, using the power rule, that's going to be positive 4200 h to the negative 3. And so 4200 over h cubed, well, that's always greater than 0 because height has to be positive. So 4200 divided by a positive number is always going to be positive. If the second derivative is always positive, then p is always concave up. So if I'm concave up, then any critical value is going to be a minimum, right? So we've convinced ourselves like this critical value is in fact the min. And so now we're going to use that h value to find, well, what is the minimum amount of fencing needed? If h was equal to 10 rad 3, then we take that and plug it in to the perimeter formula as a function of h. So that would be p of 10 rad 3, that's 2100 over 10 rad 3 plus 7 times 10 rad 3. So the 10 and one of these zeros cancels. We get 210 over rad 3 plus 70 radical 3. We can rationalize this. We can multiply the top and bottom by rad 3. We'll get 210 rad 3 over 3 plus 70 radical 3. That's actually 70 rad 3 plus 70 rad 3. So we get 140 radical 3 as our total perimeter in yards. And that's our exact answer. If we want to approximate that, just to get a sense, it's about 2, if I round up, because of course I would need more material. It's 243 yards. That's how much fencing I would need in order to create this field with this partitioning equal to 1,400 square yards total. In this next example, we're going to find the area of the largest trapezoid that can be inscribed in a circle of radius 1 and whose base is a diameter of the circle. So we are trying to maximize, so we have largest trapezoid, maximize the area of the trapezoid, but our constraint, our restriction, is that the trapezoid is inscribed, it lives inside of a circle of radius 1, and the base of the trapezoid is a diameter of the circle. So let's go ahead and draw what's happening. So as a reminder, a trapezoid has a base 1, a base 2, and a height. So I've drawn a trapezoid inside of a circle of radius 1. The circle is on the xy plane, so we can clearly see that the radius is 1, with the base along the diameter of the circle. So remember that we are trying to maximize the area. So the formula for the area of a trapezoid is given by A equals 1/2 height times base 1 plus base 2. But what we want to do is we want to go ahead and make a connection to this point xy that's on the circle and also one of the vertices of the trapezoid. So over here in the area formula, we're going to go ahead and recognize that h, the height of this trapezoid, would be given by the amount y, the y coordinate of the point. That's how much I go up. So height is y. So I have so far that area is 1/2 y. And then base 1, so the base of this top part here, remember that this distance would have to be x. So this is x and this is x. So the whole distance across here for my base 1 is 2x. So I have 2x plus my base 2 all the way across here. If the radius is 1 unit in each direction, this entire base is 2. So base 2 is 2. So I now have my area formula in terms of x and y. I need it in terms of just one of those variables. So that's why we need to come over and find a constraint equation. The constraint equation is the equation of the circle. So the equation of a circle centered at the origin with a radius of 1 is x squared plus y squared is equal to 1. Now I'm going to solve for one of the variables. I'll solve for y. So y squared equals 1 minus x squared. So y equals plus or minus the square root of 1 minus x squared. And I can't take the square root of each piece. So here I have two different equations that came out, two different functions, positive radical 1 minus x squared and negative radical 1 minus x squared. So the positive part is the top of the circle. So y equals the square root of 1 minus x squared is the top of the circle. And the negative in front would be the bottom of the circle because it would be a reflection. So since I've constructed my trapezoid on the top of the circle, I'm going to choose this equation to substitute in to this y over here. So here we have our a as a function of just the variable x, so we can consider this a of x now. And I'm going to clean it up a little bit. This 1/2, if I distribute it into this binomial, would cancel out both of these 2's. So a is now the square root of 1 minus x squared and then times x plus 1. So this is my a of x, and I want to find a prime of x, which is going to require both a product rule and a chain rule. So a prime of x is the first function, 1 minus x squared, times the derivative of the second, so that's just 1, plus the second function, x plus 1, times the derivative of the first function is where my chain rule is. So I have 1/2, 1 minus x squared to the negative 1/2, times the derivative of the inside minus 2x. So now it's a matter of simplifying this derivative so that we can find critical values. So let's go ahead and simplify this. We get the square root of 1 minus x squared for the first term, plus, let's see, the 1/2 and the 2 are going to cancel. So I have a negative x and an x plus 1 in the numerator. So I have negative x, x plus 1. And in the denominator, I have the 1 minus x squared to the positive 1/2 when I bring it to the bottom. So I'm going to rewrite that as the square root of 1 minus x squared. And now I want these to have common denominators, so I'm going to multiply the denominator over here by radical 1 minus x squared, and that's the same as the numerator here, so I'm just going to write it as that numerator squared. And let's see, that's going to give us 1 minus x squared minus x squared minus x, so I'm distributing this x here, all over radical 1 minus x squared. So I have 1 minus x minus 2x squared in the numerator, all over the square root of 1 minus x squared. And I want to know, where is this equal to 0 or undefined? So that means I'm going to need to set the numerator equal to 0 and figure out potentially where the denominator equals 0. So I have 1 minus x minus 2x squared is equal to 0, and this factors to 1 minus 2x and 1 plus x. So it gives me x equals positive 1/2 and x equals negative 1. And then we'll set the denominator, radical 1 minus x squared, equal to 0. So that's just 1 minus x squared equals 0. And that gives me just x equals both positive 1 and negative 1. But negative 1 and positive 1 both don't make sense. They both don't work. So if I go back just for a second to the picture, if I think about letting x equal either 1 or negative 1, I'm not actually going to have a trapezoid. So x was this distance here. So if I let x equal 1 or negative 1, I'm going to have just a flat line on the x-axis. I won't have a trapezoid. So now, let's go ahead and go back. The only critical value that I have is positive 1/2. So all of these are not critical values. We just have positive 1/2. And now we'll go ahead and justify that 1/2 is going to be a maximum value on this particular function. So let's go ahead and draw ourselves a number line. And that number line is only going to extend from 0 to 1, because those are really the only potential values that we could have for x. So, and in fact, I can't actually even have 0 and I can't have 1 because there would be no trapezoid at that point if we let x equal 0 or 1. So our critical value is 1/2. If we pick test points like 1/4 and 3/4 to substitute into a prime to find out about a. So let's see, this is the most simplified version of a prime, or maybe even with the factored version in the numerator. But if we substitute in 1/4, we end up with a positive, meaning a is increasing, and substituting in 3/4 gives us a negative, meaning that a is decreasing. So we do in fact have a maximum at x equals 1/2. And now we need to make sure and answer the question. So the question was to find the area of that largest trapezoid. So we know that the area is going to happen or have a maximum at the x value 1/2. So let's go back and recall that the area function that we got was 1 minus x squared in the most simplified version times x plus 1. This is our area function for every x. So if the max happens at 1/2, then we're simply going to substitute 1/2 into every x. So 1 minus 1/2 squared, and then 1/2 plus 1, which is the square root of 3/4 here, times 3/2. So we end up getting 3 radical 3 over 4. And we weren't given any specific units here, but since this is an area, we'll go ahead and write units squared. In this example, we want to find the volume of the largest right circular cone that can be inscribed in a sphere of radius r feet. Let's start by drawing a diagram. This is a three-dimensional optimization problem. I have a three-dimensional cone inside of a three-dimensional sphere. But what we're going to go ahead and do instead is draw a two-dimensional version of this where I imagine I'm looking at it from a side view. So a side view of a sphere would look like a circle. And then if a cone was inside of that circle, it would look like a triangle. So I'm going to go ahead and sketch this triangle inscribed inside of a circle, because that represents the cone that's inside of the sphere. Okay, so just quick two-dimensional image. Now what we're told is that the radius of the sphere is capital R feet. So capital R is considered to be a constant, but we don't know exactly what that constant is. Now the radius, of course, is the distance from the center of a circle to any point on the circle. So I'm going to go ahead and put the center of the circle here. And a lot of times when we draw the radius just on a random circle, we go directly to the right to indicate that's the radius, but because I'm going to want to relate the triangle to the circle, instead of drawing the radius as from the center, directly to the right, I'm going to go from the center to one of the vertices of my triangle. So now I'm starting to relate the circle and the triangle together through the radius. So I'm going to go ahead and sketch the radius here and call that capital R. So what we're trying to do is we're trying to find the volume of the largest right circular cone. We're trying to maximize this cone, or specifically its volume. So that's what I'm going to go ahead and write out. What I'm trying to do is, maximize the volume of a cone. And this cone has a constraint, though. This cone is forced to fit within the sphere. So that's the constraint. That's the restriction that I have. So my constraint is on the sphere. Or I'm going to put circle because of how we've drawn it two-dimensionally. So that's going to be my constraint. So let's talk about the equation for the volume of a cone. The equation for the volume of a cone in general is 1/3 pi times the radius squared times the height. So we're talking about the radius of the cone. So here, if this was a three-dimensional cone here, I'm going to kind of draw it and then erase it. Like if this was three-dimensional, what we're talking about with the radius is right here. So I'm going to erase that. We're thinking about it two-dimensionally. But the radius, little r, because we already have a capital R, the capital R is the radius of the sphere, but little r is the radius of the cone. So that's going to be from here over. So we have a little r, we have a capital R, and then the height of the cone goes, directly from that point all the way straight down. So I'm going to go ahead and sketch that and label that as H. Okay, so we want to make sure that, we wrote an equation, but we don't just want to write an equation without the variables matching and corresponding with our diagram. All right, well, the issue is that we want to take the derivative of this to find critical values to find a maximum, but it has
two variables involved, and so we have to eliminate one of the two variables. So we have to eliminate either r or h. So that's where the constraint comes in. So that's where we have to relate somehow this cone to this sphere, right? We have to relate the cone to the sphere. And so I mentioned, you know, how we're going to relate this. It comes from the radius of the circle. So we went from the center of the circle to, instead of any random point, I picked one of the vertices of the triangle to connect them. And so I can see, hopefully, how there's this right triangle involved that relates the triangle and the circle. So I'm focusing on, let's see if I can use a highlighter, this right triangle that's involved. So this includes all of my variables. It includes my h and my r, my little r, my h, and my capital R. Or at least it's going to include my little h in a second. So the problem is that h represents the full height of the cone, but I am interested in just this height right here of this tiny little triangle. So let's remember that I arbitrarily chose to go from the center to this vertex of the triangle. I could have went from the center up to the vertex directly above. So in other words, this is also a length of r. So if this whole entire thing is h, and this little piece right here is capital R, then this piece that I'm looking for in this tiny right triangle right here would have a height that is little h minus capital R. So again, this whole entire height was little h, and then the distance from the center to any point on the circle, even this point up here, is capital R. So if I want this height of my tiny little right triangle, I can just subtract h minus capital R. That would be this height here. And now I have all three sides of a right triangle, so how can I relate those together? Through the Pythagorean theorem. So my constraint equation is the equation of a circle. And the equation of, it's the Pythagorean theorem. And so the Pythagorean theorem is r squared plus h minus capital R squared, so little r squared, plus h minus capital R squared equals capital R squared. Okay. So now we have this constraint equation. It relates all the variables. It relates the r and the h. It relates the capital R. But capital R is not a variable. Capital R represents a fixed value. So we definitely want to remember that. In fact, I'm going to write that up here, that r is fixed. We don't know what it is, but it's fixed. It's not a varying radius. So we want to eliminate one of the variables here, either r or h. And the easiest one to actually replace is going to be r squared. Because if I look at this equation over here, I could simply subtract this quantity on the right to the other side to solve for r squared. So r squared is little r squared is equal to capital R squared minus the quantity h minus capital R squared. And then I can go ahead and plug that in now over here, right, into this r squared. And I'm going to end up with v is equal to, I'm going to go ahead and put pi over 3 just to start condensing things a little bit. So pi over 3, and I'm actually going to put the h in the front right now too. So I'm going to put pi over 3 times h, and then we have times this quantity, capital R squared, minus the quantity of h minus capital R squared. So I replaced little r squared with my solved constraint equation. All right, so now my volume equation, my primary equation, it only has one variable in it, which probably sounds weird because you see this capital R, but capital R is not a variable. Think of it as a number. Think of it as the number 10. It's a fixed value, we just don't know it. So we really truly do have only one variable in this equation, which means we can move forward with differentiating. We can move forward with taking the derivative, keeping in mind that h is the only variable. Now when looking at this equation, I have a product rule involved. So I have pi over 3h, a function of h, and then over here I have a function of h as well. So I'm going to go ahead and move forward with taking the derivative using the product rule. So we have v prime of h would be the first function pi over 3h times the derivative of the second. Now the derivative of r squared is 0 because r is a constant, right? The only variable is h. So this part is 0. This piece requires a chain rule. So I'm going to bring that 2 to the front. So I'm going to have -2 quantity h minus capital R to the first. We reduce the power by 1. The derivative of the inside is 1 minus 0. The derivative of h is just 1. R is a constant, so it's 0. So that's first d second, right? And then plus the second function, which would be r squared minus quantity h minus r squared, and then times the derivative of the first function, which would be just pi over 3, the number in front of h. Okay, so we've done the product rule now, and now we want to be able to simplify this so that I can set it equal to 0. So what I'm going to go ahead and do here is start to distribute, or actually, let's see, the first thing I'm going to do is factor out the pi over 3. So there is a pi over 3 in common in both. Let's do that. Unfortunately, I cannot factor out the quantity h minus r, capital R, because this is subtracted right here, and so it's not a factor, right? So I can only take out factors. So let's take out the pi over 3, and that should make it a little bit cleaner. So what I'll have is -2h times the quantity h minus capital R, plus we'll have capital R squared minus the quantity h minus capital R squared. So I factored out that pi over 3, so all that was left with this term, and it doesn't need parentheses around it because it's just being added, each of these terms. Okay, so now inside here, it's like, can I do anything? Can I combine anything? I can't, so the only sort of thing left to do is to start to distribute things out and hope that stuff cancels. So I'm going to distribute the 2h in, and then I'm going to distribute out quantity h minus capital R squared. So let's do that, right? So I'm distributing here. So I'd get pi over 3 -2h squared plus 2hr plus r squared minus, okay, so what's going to happen here, this foils, right? H minus r times h minus r, and then there's a negative in front of it. So we'd have h squared minus 2h capital R plus r squared. So here I just, multiply that out, and then the negative though is going to distribute. So that's why I kind of did it small up there. So I have minus h squared plus 2h capital R minus capital R squared. Okay, so now that it's just a whole bunch of terms added or subtracted, our hope is that that leads us to canceling some stuff out, and it does. So r squared and minus r squared give us 0. And then we can combine some like terms. So -2h squared minus h squared is going to combine together. So let's see, let's leave this pi over 3 in the front. We're going to have -3h squared, and then we also have plus 2hr plus 2hr are like terms, for a total of plus 4h capital R. So this is much better in terms of a simplified derivative that we can now attempt to set equal to 0. So I'm going to make some space here. This is definitely a long problem. So I'm going to set this equal to 0. So 0 has to equal pi over 3 times -3h squared plus 4hr. And so what I want to do is factor out an h, right? This is a quadratic essentially, like h squared plus 4h. So let's factor out that h. And we'll have -3h plus 4r left, and then I can set each piece of the product equal to 0, right? When I factor, I create a product. I could set each of these equal to 0. So I end up getting h is equal to 0. And then here, if I set negative 3h plus 4r equal to 0, I'm solving for h. So I'd get negative 4r equals negative 3h. So h is equal to 4/3 r. Okay, so this is my critical value. Well, technically, there's two critical values, right? 0 and 4/3 r, which remember is a number because r is some fixed value. So this critical value, 4/3 r, is the one we're going to move forward with because h being 0 doesn't make sense, right? Because this is a height. So this one doesn't make sense. We're not going to use it. We're going to move forward with h equals 4/3 r, right? So this right here is my critical value. Now we do, technically want to make sure that this is a minimum, right? So, or maximum, sorry, we're trying to maximize something, sorry. So we want to show that this is going to be a maximum value. So let's go ahead and see if we can fit that work in here. So just showing that we truly do have a maximum. Well, let's go ahead and take the second derivative of v and see what's going on with that so we can truly show this is a maximum value. So the second derivative, let's use the most simplified version we got to, which would be right here, right? So let's see. Actually, I'm going to put v prime of h. I'm going to write this as negative 3 pi h squared plus 4/3 pi hr. So what's happening right here is I just thought about distributing this pi over 3 in for a second into v prime so that the 3's would cancel. I get negative, oh actually the 3's would cancel, sorry about that. So it'd just be negative pi. Okay, so negative pi h squared and then plus 4/3 pi hr. So I just distributed this in because I want to use the power rule right now. That's what I'm trying to do. So I didn't want this pi over 3 in the front to create like a product. I just want to distribute it in real quick so that I can do the second derivative using the product rule. So that's going to be negative 2 pi h plus 4/3 pi r. So let's use the second derivative test here, plug in the critical value into the second derivative and see what happens. So if I do v double prime of 4/3 r, I'm going to get negative 2 pi times 4/3 r plus 4/3 pi r. I'm plugging that 4/3 r into the one and only h that we have right here. And then we'll see what we get. So we get negative 8 over 3 pi r plus 4 over 3 pi r. These are like terms, so we get negative 4 over 3 pi r. Well, if the second derivative at a critical value is negative, right, this is less than 0, then my function must be concave down, right? So that means that like v is concave down. So if I have a concave down function, then I do truly have a maximum. So I have a maximum at my critical value of 4/3 r. So we've now shown that that's true, that we really did find our maximum value. So then it's a matter of answering the question. Let's go back up. Find the volume of the largest right circular cone that can be inscribed in this sphere. So I want to find that volume. Well, let's see. We'll use the equation that had only h's in it, and we're going to substitute in the h, the height, that we know yields the biggest volume, because we just showed it yields the biggest volume. It's a maximum. So we're going to plug our h value, 4/3 r, into this equation here and then simplify it. So let's make some space for that. Look at that, we completely ran out of space on this problem. So let's see. Our volume formula as a function of h was pi over 3h times the quantity capital R squared minus the quantity h minus capital R squared. So we know now that the maximum occurs at 4/3 R. So we're going to plug that 4/3 R into each h here. So we get pi over 3 times 4/3 R times the quantity R squared minus the quantity 4/3 R minus R squared. And let's keep simplifying. So 4 pi over 9R, quantity R squared minus, all right, 4/3 R minus 1R. 4/3 minus 1 is 1/3. So we get 1/3 R squared. And we get 4 pi over 9R, quantity R squared, minus 1/9 R squared. So 1/3 squared is 1/9. Let's see, this is 1 R squared minus 1/9 R squared. That's 8/9. So 4 pi over 9R times the quantity 8/9 R squared. Woo! And let's see, now we get what? 32, 4 times 8, pi over 9 times 9 is 81, R cubed. 32 pi over 81 R cubed would be the maximum volume of that cone. So since we were talking about feet, the units would have to be feet cubed because we're talking about a volume. And that is our answer. And it was a lot of work. It was. These are very deceiving little problems because look how tiny the problem was back here, right? Just find the volume of the largest right circular cone that can be inscribed inside a sphere of radius r feet. Just like one simple sentence turned into all of this work, right? But it's about understanding like what we're trying to do first, like maximize what? Maximize volume. Okay, we need the volume formula. It has two variables. How do we get rid of one of them? Well, we always need a constraint equation. The constraint equation is, on this example, like a known formula. It ended up being the formula of for the Pythagorean theorem, excuse me, because we used a right triangle to involve all of the variables, little r, little h, and capital R. And then solving that constraint to plug it back in. Then it's a derivative. The derivative looked ugly, but it was really just a product rule and a chain rule, and a pretty simple one. It just looked ugly because that capital R was in there, but it was really just a placeholder for a specific number. But it made things a little bit trickier to keep track of. We got to our critical value, 4/3 capital R, right? It had an R in it, but it's still just some number as a critical value. We showed, using the second derivative test, that that critical value must have been a maximum because my function was concave down. And then once we proved it, now let's use it to find the actual volume. So we just plugged that critical value into our volume function and simplified as much as we could. Again, we still had an R in our answer, but R just represents some fixed number. So this really is acting like a numerical answer.